Welcome to TrendSpark. Here is the newest SignalSpark. Today's topic is SpaceX's wildest plan may not be Mars. It may be AI in orbit. Picture the stack. AI chips made in Texas. Giant compute satellites launched by Starship. Solar arrays wider than an airliner. Laser links moving results around Earth. SpaceX now describes all of it as one system. And in January 2026, it asked the FCC for authority to operate up to 1 million orbital data center satellites. That number needs a warning label. The FCC accepted the application for public comment. It did not approve 1 million satellites, and SpaceX has not published a schedule to launch that many. But the filing is real. It covers orbits from 500 kilometers to 2,000 kilometers and a network built mainly around optical links. The hardware has a name: Starmind. SpaceX's current AI1 page lists a 75m wingspan, a 30m deployed height, and up to 175 kilowatts of average compute payload. A planned gigasat factory in Bastrop is intended to start producing thousands of AI satellites as soon as late 2027. Those are company plans, not machines already running above us. Why send a data center to space? Because building one on Earth is becoming a fight over grid connections, land, permits, and cooling. In a suitable sun-synchronous orbit, large solar arrays can collect power for much more of the day. Starship could deliver the mass. Starlink could carry the answers home. At least, that is the pitch. Here is the first physics plot twist. Space is not free air conditioning. Vacuum has no air, which means no fans and no convection. Every watt used by a processor becomes heat. That heat must travel into radiator panels and leave as infrared radiation. NASA calls deployable radiators challenging because spacecraft have limited surface area and volume. More compute means more power and more radiator. SpaceX says removing chillers, cooling towers, and fans could cut cooling power overhead by an order of magnitude. That could be valuable. But the radiator itself still has mass. It must avoid sunlight, and it has to survive launch and years in orbit. The cooling bill does not vanish. It changes shape and gets strapped to a rocket. Then comes the network. SpaceX reported more than 23,000 inter-satellite lasers in the Starlink constellation by March 2026. Starmind would use a laser mesh to move data and return results to Earth. That architecture looks promising for inference, taking a trained model and asking it to process new information. Training a frontier model is much harder because thousands of processors must exchange enormous amounts of data with extremely low delay. A July 2026 engineering analysis reached a careful conclusion. Orbital inference may be feasible, but frontier-scale training is unlikely to beat terrestrial data centers under current cost and network assumptions. That is one preprint, not the final word. Still, it points toward a realistic first job. Process satellite imagery and other space-generated data before sending only the useful results down.
So the cloud is becoming an actual cloud. Was that the plan, or did marketing finally win?
The chips are the next bottleneck. Terafab is a collaboration involving SpaceX, Tesla, and Intel. The goal is to bring logic, memory, and advanced packaging under one roof and eventually produce 1 TW of compute hardware per year. That is an extraordinary target. SpaceX's own SEC materials also say specific project timelines, milestones, and capital spending have not yet been determined. Those filings add another useful reality check. SpaceX still expects to buy a significant share of its compute hardware from outside suppliers. Terafab is not a finished chip factory waiting for a ribbon. It is an attempt to build the missing layer in a vertically integrated machine: chips, satellites, rockets, lasers, and AI services controlled by related companies. That integration is why the proposal deserves attention. SpaceX already mass-produces satellites, operates a global laser network, and launches more orbital mass than any competitor. If Starship becomes rapidly reusable at the cost and cadence SpaceX targets, the company could test orbital compute sooner than almost anyone. But each "if" is carrying several tons of engineering. Maintenance is one of them. SpaceX says it does not expect to repair failed processors in orbit. Instead, software would route work around broken hardware. Radiation, micrometeoroids, solar array degradation, and obsolete chips become fleet management problems. On Earth, a technician can replace a server. In orbit, your repair plan may be launch another data center. Scale creates a second problem. Up to 1 million satellites is a regulatory ceiling, not a forecast. Even a small fraction would transform traffic in low Earth orbit. Collision avoidance, failed satellites, astronomy, launches, and controlled disposal all become harder. ESA says the atmospheric effects of megaconstellation launches and reentries are still not fully characterized or regulated. So separate the layers. Documented, the FCC application, the Starmind design, the Gigasat plan, Terafab's partnership, and SpaceX's existing laser network. Plausible but unproven, useful orbital inference at competitive cost. Aspirational, 1 TW of chip output, millions of tons launched each year, 1 million compute satellites, and eventually lunar factories. The near-term question is not whether SpaceX will move all AI into orbit. It is whether the first orbital computers can do one job better than an Earth data center, perhaps processing imagery, weather, communications, or autonomous spacecraft data where it is created. If that works, Starmind becomes infrastructure. If it does not, it remains the most expensive way ever invented to avoid a building permit. Would you trust AI infrastructure above Earth, or should the cloud stay on the ground? Tell us what we missed and what TrendSpark should improve in the next investigation. We read the feedback. Chase the signal.
Like what we're making. Keep chasing the signal. Watch this story here, or this one over here.